Hello dear students, welcome back to my lesson. Today's lesson, we're going to explain the self-induction in chapter 6, section 1. Self-induction, its definition is the creation of induced EMF. Creation what? Induced EMF or induced current in a circuit due to what? Due to variation of its own current. So it means that the self-induction is a result as a change of the current, the magnitude of the current. Okay. According to this equation, EMF is equal to negative L delta I over delta T. This is the equation of self-induction. The self-induction, the EMF is induced as a result of changing what? Changing the current. So to proving this equation, we have, for example, a coil, okay, and a magnetic field, okay. For example, when the current carrying or wrapping in this coil, for example, like that, assume that the current is moving in this direction. This is the direction of the current, and here the direction is downward here, and here the direction of the current is upward. So in this end, the current goes below the coil, below the rod, and the direction of the current is downward. The direction of the current is downward according the right hand rule. The four fingers pointing below this coil, and it goes above the coil downward like that according to the right hand rule. The direction of the current is like that. So here this is magnetic field, okay. When the current carrying into this wire, the magnetic field is produced. According to this equation, magnetic field is equal to mu naught Ni over L in a solenoid, okay. According this equation, what is the relation between the current and magnetic field? It is directly proportional, okay. When the magnitude of the current increases, what happens to the magnetic field? Also increases. So according to this equation, we can obtain this change. So when the magnetic field increases, the change in magnetic flux also increases. So it means that change in magnetic flux is directly proportional to change of the current. More change of current, more magnetic field. More magnetic field produces more change in magnetic flux. So if we multiply both sides by negative n, the equation becomes like that. Negative n flux is directly proportional negative n delta I. And if you divide both sides by t, it becomes like that, negative n change in flux. Now I'm going to prove this equation, okay. Change in flux per unit of time is directly proportional negative n delta I over delta t, okay. If you see that, what is this? This is the equation of EMF. Induced EMF is equal to what? Negative EMF according to Faraday's law is equal to negative n change flux per unit of time. Instead of this, we can write EMF, okay. If you convert directly proportional to the equal, we have to add a constant, negative n times constant according math basic, okay. For any time when you change the directly proportional to the equal, so you have to multiply this variable by constant, okay. Delta I over delta t. So finally EMF is equal to negative n times constant is equal to L. What is remain here? Delta I over delta t. So what is this? This is the equation of EMF in a self-inductance, okay. And when the magnet of the current increases, what happened to the magnetic field? Also increases. And what happened to the change in magnetic flux? Also increases. Now I'm going to explain in detail what is the self-inductance. So how the self-inductance is working. And what is the importance in self-inductance? Okay, look at me. For example, if we have a circuit, a battery, okay, what is this? This is battery, positive terminal and negative, okay, connected with the switch. What is this? This is the switch, okay, and the circuit is connecting with the light bulb, for example, with a resistance. In the case when we close the switch, what happened? The current is closed and the light bulb is all shining. So there is no surprising here, okay? But what is the surprise here? For example, if we connect it self-inductance, for example, like, what is this? This is self-inductance, okay? This is induction. If we connected the induction here with the light bulb, look, what is this? This is the light bulb, okay? Look, when we close the switch, what will happen? The current increases. The current, what happened to the current? The increases. So whenever the current in the coil or in induction increases or decreases, the magnetic field also increase and decrease. When the magnetic field decrease and increase, it means that there is a change in magnetic flux. When the magnetic flux changes, the current induced in the coil or EMF is induced in the coil. So the induced EMF or induced current in the coil is opposite to the EMF of the source, okay? Look, when we close the switch, in the case of close the switch, sorry, this is light bulb, okay? Okay. When we close the switch, in the case of close the switch, okay, when we close the switch, what happened to the current? The current changes, the current increases. Change in current, what happened to the change in current? Increases. When the change in current increases, what about the magnetic field? The magnetic field also changes, increases, okay? When the magnetic flux increases, the magnetic flux also increases. So this magnetic flux induces the current. Induce what? The current, okay? So this induced current is opposite to what? Is opposite to the change the current in the source, okay? So it means that the coil heat is what? Heat is the change in the current, okay? But in the case when the current does not change, no current is induced in the coil. Why? Because there is no change in the current. If you know that, so the induced EMF in the coil or in induction is a result of what? Change in the current. When change in current is zero, EMF also zero. So when does the current or EMF is induced in the coil? When the current changes. So in the case of switch, close the switch, the current goes through the circuit and the glowing of the light bulb takes time, okay? So this glowing takes time. Why? Because when the current is carrying into this coil, okay, this coil also induces the current, okay? So this current, in the case of increasing the current, is opposite to what? To the current of the increasing the change of the current in the source, okay? So what about in the case of in the case of the close the switch, both sides becomes opposite, okay? So the potential difference is produced here. The potential difference is produced here. It becomes positive, and here becomes negative. So positive with this is the polarity. Positive with positive is they repel each other and they becomes the opposite direction of the current. Okay, so this is in the case of increasing. But in the case of when we open the switch, what happened to the current? Delta I decreases until reaches zero. When the current decreases, the coil hates the change of the current. In the case of increase or decrease, the current is induced. Okay. The magnetic field also decreases. Change magnetic flux also decreases. So the current is induced. The current is induced. Why? Because the flux changes. So this current opposes, the induced current in the coil is opposes what? The changing of the current in the source. Okay. So in this case, the current of the induced current in the coil and the current of the source, they become the same direction. Same direction of the current, the same direction of the current. The EMF has a largest maximum, or the largest value, maximum value. Why? Because when the current decreases, it becomes negative. Okay, negative times negative, it becomes positive. What does the positive sign indicate for potential difference? It means that the potential difference increases. So that is why sometimes when you switch off the heater, at home, so you can see the spark on the plugs. Okay, what is the meaning of the spark when we switch off suddenly? When you switch off suddenly of the plug of the heater, you can see the spark. This spark indicate what? This spark indicates that the change of the current decreases according to Lenz's law. The current in the coil opposes to this decreasing, so that is why the EMF becomes more and more value. Okay. Now I'm going to prove the coefficient of self-inductance. A coefficient of self-inductance, L is equal to what? L, the coefficient of self-inductance, is equal to mu naught n square A over L. What is this? This is the equation of self-inductance. Okay, coefficient of self-inductance. For example, if this is coil, okay, and okay, so okay, when the direction of the current is here is downward, this is the current, and here is upward according to the right hand rule below the coil at downward. So here becomes north pole and this becomes south pole. Okay, so the coefficient of self-inductance, what does the coefficient of self-inductance depend on? It depends on the permeability. Okay, and it is directly proportional, and the number of turn and the area of the coil with the length of the coil. What is this? This is the length of the coil. So how can you prove this equation? This equation came from this. According the self-inductance, change flux is directly proportional, or EMF is equal to what? L change current per unit of time. EMF is equal to what? Is equal to negative N flux per unit time is equal to negative L delta I over delta T. Okay. So delta T cancel with delta T, negative cancel with negative. What does remain? Flux and flux is equal to what? Li. Okay, and flux is equal to what? Li. Why? Because delta T cancel with delta T and negative cancel with this negative. If you arrange this equation, L is equal to what? L is equal to N flux over I. Okay, so as you know, flux is equal to what? Is equal to AB. And this is solenoid. The magnetic field of solenoid is equal to what? Mu naught Ni over L. Okay, as a result, you can see that L is equal to what? N times, instead of flux, write AB. Okay, AB over what? Over I. And N times A times B is equal to what? Mu naught Ni over L. Instead of this, we write what? Mu naught Ni over L, and already we have current here. Okay, current with current cancel. N times N square. What does remain? L is equal to mu naught N times N square A over L. So it means that the coefficient of self-inductance depend on the permeability, number of turns, square of the number of turns, area of the coil, and length of the coil. If they bring in the exam, in the Wizari exam like that, the coefficient of self-inductance is inversely proportional with of the following. The permeability, no. The square number of turns, no. Area, no. The length of the coil, yes. What is the relation between the coefficient of self-inductance with the length? Is inversely proportional. Okay, so what is the relation between the coefficient of self-inductance with the permeability? Directly proportional. With the square of number of turns? Directly proportional. With the area of the coil? Directly proportional. Okay, according to this equation, which one has more effective to increasing the coefficient of self-inductance? By increasing permeability, or by increasing area, or by increasing number of turns? Absolutely by increasing number of turns. Why? Because coefficient of self-inductance is directly proportional to the square number of turns. In the case when number of turns increases by factor of 2 or becomes double, the coefficient of self-inductance becomes quadruple. In the case when the number of turns increases by factor of 3, the coefficient of self-inductance becomes 9 times. Okay? But with the area and the permeability is directly proportional without square. Okay? So this is the coefficient of self-inductance. If we continue here, the definition of self-induction, the creation of what? Induced EMF in the circuit due to what? Due to the variation of what? Of its own current. And EMF in the self-inductance is equal to what? Negative L delta I over delta T. And delta I is equal to I final minus I initial. At constant current, EMF is 0 in the coil. In the case when delta I over delta T increases, it becomes negative. And EMF becomes positive. Okay, in the case of decreasing the current. And when the change in the current period of time increases, it becomes positive, and EMF is negative. Why? Because according to Lenz's law, the induced current in the coil is opposite the change of the current in the circuit. Okay, so if the current is reversed, I final is equal to negative I initial. Okay, so the resultant EMF is equal to the applied EMF, electromotive force, minus induced EMF. So we prove this equation. Okay. So the self-inductance is as a result of what? Changing the current or changing magnetic field. Look at this experiment. What we have in this experiment? We have a galvanometer. This is what? This is galvanometer for reading the current, very low current, and connected with the battery. Okay, so this is the switch, and this is rheostat. What is rheostat? The rheostat is a device that can be using for changing the magnitude of the current. By rheostat, we can increase or decrease the current. Why? Because when the rheostat, the resistance increases, the current decreases. When the resistance decreases, the current increases. Okay, inversely related. And we have a coil here. What is this? This is the coil. Okay, and this is magnetic core. What is this? This is magnetic core. It means that the mu naught, or mu, sorry, not mu naught. Mu naught for the air. This is mu. What is the relation of the magnetic field with the mu, with the permeability? The permeability has directly relation with the magnitude of the magnetic field. When the permeability increases, the magnetic field also increases. Okay? So we move the rheostat until the ammeter point is to 50 milliampere. Okay, so we can control the magnitude of the current by rheostat. We have to remove the rheostat until the ammeter point is to 50 microampere. For example, when the coil or when the magnetic core, when the magnet is connected, when the magnetic core is connected, what happened to the mu? Increases. When the mu increases, what happened to the magnetic field? The current is constant here. Here, the current is constant, okay? At constant current. Constant current. When connecting the iron core, or the magnetic core, sorry, it means that we're increasing the permeability. When the permeability increases, what happened to the magnetic field also increases. Why? Because B is equal to what? Is equal to mu N I over L. When mu increases, what happened to the magnetic field also increases. When the magnetic field increases, flux also increases and changes. So when the flux changes, the current is induced. Okay? The current is induced. So this current is opposite to the current of the source. Okay? So the increasing of the current, it means that delta I is positive. And EMF in coefficient in self-inductance is equal to negative L delta I over delta T. When delta I is positive, positive times negative is equal to negative. It means that the reading, the potential difference decreases, the current also decreases. So the reading of the ammeter should be drops. Okay? So when does the reading of the ammeter drops in self-inductance? By connecting the magnetic core or by removing the magnetic core? Absolutely, by connecting the magnetic core. Why? Why when we are connecting the magnetic core, the current of the galvanometer reduces or drops from 50 microampere? Because this increasing of the magnetic field by connecting the iron core, it goes to increasing the magnetic field. Increasing magnetic field, it goes to increasing the change in magnetic flux. When the magnetic flux change increases, the induced current and induced EMF increases. So the coil is, they heat this changes in the current. That is why they opposite to the source and the current drops from 50 microampere. Okay, so look, when we're connecting the magnetic core, the reading of the ammeter drops. What do you mean by drops? It means that decreases. Okay, so when does the reading of the ammeter drops? In the case of connecting the magnetic core or connecting the magnetic core. Okay, indicating decrease in what? Decrease in the circuit. Okay, decrease in the circuit, current in the circuit. Okay. Oh, the second case, when the coil is removed or when the magnetic core is removed, it means that mu is decreases. When permeability decreases, what happened to the magnetic field? Look, this is by connecting magnetic core. But the second case, when we remove the magnetic core. When we remove the magnetic core or the coil, what will happen? In that case, the permeability decreases. When the permeability decreases, the magnetic field also decreases. When the magnetic field decreases, the magnetic flux change in magnetic flux also decreases. When the change magnetic flux decreases, they produces the EMF, okay, on the current or induced current also decreases. Look, the current decreases. And this decreasing of the current is opposite to the source, and opposite to the source of the circuit, this battery. So this decreasing of the current, it goes to increasing the current. So it means that in that case, the ammeter reading more than 50 microampere. Okay, so when the coil is removed, the current increases temporarily. Why? Because this is DC source. In DC source, only during the switch off or switch on the switch, the current changes. Okay, due to decrease the magnetic flux. So here, but when we're removing the magnetic core, okay. So the conclusion of the first step in this experiment: when does the reading of the ammeter drops? When we are connecting the magnetic core. So when does the reading of the ammeter increases or the current increases? When the magnetic core is removed. Okay. Also, if the intensity of the current is increased or decreased, it means that when the current is changes in the circuit, the magnetic flux crossing the turns of the coil will vary, or also will changes. Okay, when does magnetic flux changes? When the current decrease or increase. Okay, a cell of back EMF is created when the current increases, and proportional EMF when the current decreases. Okay, according to this equation, delta I, it goes to change in magnetic flux. Why? Because magnetic field increases and the EMF is induced. So this induced EMF or this induced current is opposite any change in the current in a circuit. When the current does not change, no current is induced, no EMF is induced in the circuit. Coefficient of self-induction is always positive because the coefficient of self-induction does not depending on the change in the current. The coefficient of self-inductance or induction, coefficient of self-induction, L, we prove it, is equal to mu naught N or mu N squared A over L. Mu permeability is always positive. Number of turn also always positive. Area is a scalar, always positive, and the length is positive. That is why L can never be negative. Okay. So according to this equation, so why the coefficient of self-induction is always positive? According to this equation, EMF is equal to negative L delta I over delta T. L is equal to what? Negative delta I over delta T. EMF is in the numerator. EMF over delta I over delta T. Okay. When the EMF increases, when the current increases, okay, the EMF decrease, it becomes negative. Negative times negative, negative divided by negative is positive. So it means that there is the opposite change between the EMF and the change in the current. Okay. So when the current decreases, the magnitude of the current is negative, and here is positive. Negative times negative is positive. That is why coefficient of self-inductance is always positive, and coefficient of self-inductance does not depending on the change in the current and induced EMF. Please, coefficient of self-inductance depends on 4 factors: permeability, square number of turn, area of the coil, length of the coil. So what do we find out about the self-induction test or experiment? We found out that if the magnetic flux through a coil is varied or changes due to the variation of the current in the coil, when this variation affected the coil and leads to an EMF that resists what? Resists the variation or change of the original current of the coil itself. Okay? So this phenomena is called what? Self-induction. If a current traverses a coil, its direction changes, the magnetic flux which crosses each turn of the coil is directly proportional to the intensity of the current. Okay, and if the current varies the time rate of the current, and the flux varies at the rate delta flux over delta t, and this is directly proportional to each other. When the current is increased, or when the coil is connected, this is not removed, please correct this is wrong. When the coil is connected, okay, in that case the EMF is produced at opposites of the source. They are in opposite direction. But in the case when the current is decreased, or when the magnetic core or the coil is removed, the induced current becomes the same direction of the source to increasing the magnitude of the current. Okay. How the induced magnetic field changes? By changing the rheostat. In the experiment of the self-induction, how can you change the magnetic field? By changing the rheostat. Okay, why? Because the rheostat can control the magnitude of the current, can be used to increase or decrease the magnitude of the current, and when the current increases or decreases, the magnitude of the magnetic field also changes. Okay, so we proved this equation. Okay, coefficient of self-induction L, the ratio of the magnetic flux that crosses a circuit to the current that traverses it, the magnetic flux per unit of time. Coefficient of self-induction measured in what? In Henry. Okay, so according to this equation, E is equal to what? Negative L delta I over delta T. L is equal to what? If you rearrange this equation, E over what? Delta I over delta T. Coefficient of self-induction measured in what? In Henry. Potential difference measured in what? Volt. Okay, and the current per unit of time, it means that ampere per second. So what is the definition of Henry? So this is very important, please pay attention. The definition of Henry, the SI unit of coefficient of self-induction, is the unit of coefficient, is the unit of what? Is the unit of coefficient of self-induction. Okay, in a closed circuit or coil in which 1 volt, how many volts? 1 volt, look, 1 volt of potential difference is produced by a variation of the inducing current of 1 ampere per second. So when does 1 volt of potential difference is produced? When the changing or the variation of the current is equal to 1 ampere per second. Okay, 1 divided by 1 is equal to 1 Henry. Okay, then the magnitude of the coefficient of self-induction becomes 1 Henry. Okay, so we have many equivalent units of Henry. Okay, we have many equivalent units of Henry. Now I'm going to write some of the equivalent units of Henry. Okay, look. Okay. From this equation, L is equal to the induced EMF over the variation of the current per unit of time. L measured in what? In Henry. Potential difference measured in volt. I ampere time second. Okay. So according the math basic, if you rearrange this denominator, this second it goes up, it becomes volt second over ampere. Okay. So it means that Henry is equal to what? Volt second per ampere. And volt per second over ampere, or volt second is equal to what? Volt second is equal to Tesla meter square, and equal to Henry ampere, or equal to Weber. Okay, volt second is equal to what? Is equal to Tesla meter square. Okay, because according to this equation, flux is equal to what? Is equal to a B. Okay, according to this equation, EMF, Faraday's law, flux over time, flux is equal to what here? Is equal to EMF times delta T. Look, here, the flux is measured in what? Weber. Okay? Is equal to what? Magnetic field Tesla, A area meter square. So it means that Weber is equal to what? Tesla meter square. Okay? Here the same thing. Look, flux is Weber is equal to potential difference volt times second is equal to volt second. So it means that if these two sides are equal, Weber is equal to Weber, also Tesla meter square is equal to volt second. Okay? So, and also you can say volt second is equal to Tesla meter square and is equal to Weber per ampere. Okay? And this Tesla, according to the magnetic force, the equation of the magnetic force is equal to what? Is equal to QVB sine theta. Okay? B is equal to what? B is equal to, rearrange the equation, QV. B Tesla, force Newton, charge Coulomb. Okay, this is V, meter per second. Okay, Coulomb per second is ampere. Coulomb per second is what? Is ampere. What is remain? Meter. So it means that Tesla is equal to what? Newton ampere meter. Instead of this Tesla, write what? Newton per ampere meter. Time is meter over ampere. Ampere, it goes down, so it becomes ampere square. Meter with meter cancel. What is remain? Newton meter per ampere square. And as you know, Newton dot meter, sorry, this is not Newton per meter, this is Newton meter. Newton meter is equal to joule over ampere square. Okay? So, again from here, coefficient of self-inductance is Henry. Volt, ampere, over 1 over second. It becomes what? Ampere over second. Look, for the second part of proving the units. Look, from this equation, EMF is equal to what? Delta I over delta T. L is equal to what? EMF over delta I over delta T. Okay? Look. Coefficient of self-induction, Henry, is equal to potential difference, electromotive force measured in volt. Okay? Ampere per second. Ampere per what? Per second. And also you can write down like that, ampere times 1 over second. If you take out the second in the denominator, it becomes like that. Ampere times 1 over second or ampere per second is the same thing. Okay? Bring down the Henry. Volt. Ampere 1 over second is not equal to hertz. Yes, why? Because frequency is equal to 1 over period. Okay? Frequency hertz. Period second. 1 over second is equal to hertz. Okay? Is equal to what? Is equal to hertz. And V over A is equal to what? According to Ohm's law, V is equal to what? IR. Okay? R is equal to what? V over I. R measured in what? Ohm. Volt, volt. I, ampere. So V over A is equal to what? Is equal to R. R. Sorry. Henry is equal to what? Is equal to R over hertz. Okay? Sorry. This is not R, this is ohm. Volt per ampere is equal to what? Ohm. Ohm is the unit of resistance. And also, if you cross product, okay, ohm is equal to what? Henry hertz. Or you can say ohm is equal to Henry over second. Okay, so Henry is equal to what? Ohm second. So these are the equivalent. Henry is equal to what? Ohm second, ohm per hertz. Why? Because V over A is equal to ohm and Ohm is equal to Henry Hertz. So these are the units just for knowledge, okay? So the proving units is very important. So you cannot memorize all the equivalent units. That is why you have to prove one by one, okay? If you memorize, maybe you will forget in the exam. Okay, so that is why I suggest for all the students to memorizing by understanding, like by, for example, proving the equation, okay? Let's solve the sample problem 6a. Sample problem 6a. An air solenoid. What do you mean by air solenoid? It means that the permeability is mu naught for the air. Its length is 10 meter. Length is equal to 10 centimeter. It means that 0.1 meter, okay? Cross-section area 25 centimeters square. Be careful. Area is given 25 centimeter square. Please don't forget to converting the units. It's not allowed to solving area with centimeter square. You have to convert to meter square, multiply 10 power negative 4. Why? Because converting centimeter square to meter square, multiply 10 power negative 4. Okay? So area is equal to what? 25 times 10 power negative 4 meters squared. And 400 turns. How many turns do we have? 400 turns, okay? Is traversed or passes by a current 4 ampere. What is the magnitude of the current? 4 ampere, okay? Calculate the magnetic flux. What is unknown? Magnetic flux is unknown. Which crosses the solenoid. What is the type of this coil? Is solenoid. If the current is reversed, what do you mean by reversing of the current? It means that this is I initial is positive 4 ampere, I final is equal to negative 4 ampere. Why? Because when we reverse the magnitude of the current, here, for example, we have positive 4 ampere. If you reverse this current, it becomes what? Negative 4 ampere. Okay? During 0.1 second, calculate the induced EMF. Delta T is equal to what? 0.1 second. Calculate what? EMF. So, in this question, what is changes? In this question, the flux is produced because of the changing what? The current. So, in this question, the direction of the current changes. Okay? By changing the direction of the current, the magnetic field changes? Yes. When the magnetic field changes, the flux changes? Yes. So at first we have to find this flux. How can you find this flux? If you remember this equation, EMF is equal to what? Negative L I over delta T. This is the equation of self-induction. E, according Faraday's law, is equal to what? E is equal to negative N change flux over time is equal to what? L delta I over delta T. Okay? Time with time cancel. Negative with negative cancel. What is remain? N flux equal to what? Li. Rearrange this equation. Okay? Rearrange this equation. Flux is equal to what? Flux is equal to Li over N. Okay? So, do we have L coefficient of self-induction? No. L is equal to what? Coefficient of self-induction is equal to what? L is equal to mu naught N squared A over L. Do we have mu naught? Yes, constant, 4 pi times 10 power. L is equal to what? 4 pi times 10 power negative 7. N was given 400 square. Area 25 times 10 power negative 4 over 0.1. L is equal to what? L is equal to 5.03 times 10 power negative 3 Henry. This is Henry, okay? Henry. So, please don't be confused about this L with the length of the solenoid. The length of the solenoid is small l. but coefficient of self-inductance is a capital L. Okay. After finding the coefficient of self-inductance, you can find the magnitude of flux. The magnitude of the flux is equal to what? L. We didn't have L, but we found it. Okay, was 503 times 10 power negative 3 times the magnitude of the current was given 4 ampere divided by 400. Flux is equal to what? Flux is equal to 5 times 10 power negative 5 Tesla meter square or Weber or volt second. So these are the equivalent units of flux. Okay, in this way we can find the magnitude of the flux. This is the first part of the question, to finding flux. And flux is equal to Li according the equation of self-induction. To finding the flux, we need L, the coefficient of self-induction. The coefficient of self-induction in this question was not given, but we found it. Okay, after that we replace it and we found the flux. The second part of this question is to find the induced EMF in this coil or in this circuit. To find the induced EMF in this coil, at first you have to write down the equation. The equation of self-induction is equal to what? L delta I over delta T. To find the induced EMF, we need what? Coefficient of self-inductance, change current, and time. Do we have coefficient of self-inductance? Yes. 5.03 times 10 power negative 3 Henry. Do we have change in current? Yes. After the current is reversed, the sign of the current changes, not magnitude. In this case, the magnitude of the current does not change. The magnetic flux results through the changing of the direction of the current. Okay. I initial was 4 ampere, I final is negative 4 ampere. Why? Why the final current is negative? Because the current is what? Reversed. Okay. So you can replace EMF is equal to what? Negative 5.03 times 10 power negative 3. Delta I is equal to I final minus I initial. I final negative, please don't forget this negative. Negative 4 minus negative over 0.1. E is equal to negative 5.03 times 10 power negative 3 times negative 8 over 0.1. So the current decreases negative. Negative times negative is positive. So that is why EMF, it should be positive. Positive what? 0.4 volts. This is the induced EMF, and this is the very good question, and this is a wizarding question. Be careful, okay? Whenever the current changes or its direction changes, the magnetic field also changes, and the magnetic flux is produced and changes. Practice 6A, question 1, the easy question. Electric current grows in a circuit from 0 ampere to 10 ampere. So what is changes here? The magnitude of the current. I initial 0, but I final 10 ampere. Okay, it means that the current increases. Delta I is positive. So positive times negative, negative. So the result of the induced EMF and the current, it should be negative or decreases. The resultant current decreases. Why? Because according to self-induction, when the current increases, this increasing of the current is opposite to the source. That is why it goes to decreasing the EMF and the current of the source. During 0.1 second, time 0.1 second. If the coefficient of self-induction on the circuit L, do we have L? Yes, 0.02 Henry. Calculate the induced EMF within the circuit. So in this question, without solving, the EMF is positive or negative, and why? You have to say EMF is positive. Why is negative? Sorry, negative. Why negative? Because the current increases. This EMF is opposite the increasing of the current. E is equal to what? Negative L, change current over time, negative 0.02 times I final minus I initial, 10 minus 0 over 0.1. Negative times positive is negative. Negative what? 2 volts. Okay? So it means that the induced EMF of the coil is decreases. Which one leads to the higher increasing of what? Look. Which one leads to the higher increases or increase in the coefficient of self-induction? L of a solenoid, doubling number of turn or doubling cross-section area, and why? So for solving this question, so you have to write down the equation of coefficient of self-induction. L is equal to what? As I proved it for you, mu n squared A over L. What is relation of coefficient of self-inductance with number of turn? Is directly proportional. Okay, so what is the relation coefficient of self-inductance with the area? Also directly proportional. But which one leads to higher increase? It means that which one has more effective for increasing the coefficient of self-inductance? Number of turn or area? Absolutely number of turn. Why? Because number of turn is square in the equation. When we double the number of turn, we have square L2, it becomes 4 times L1. Increases by which factor? By factor 4. When number of turn becomes double, coefficient of self-induction becomes quadruple. Okay? But area, when we increase the area by factor of 2, the coefficient of self-inductance also increases by the same factor by factor of 2. So in that case, question number 22. This is question 2 of the practice 6A. Question number 22 in chapter review. The number of turn of the coil is doubled. What happened to the number of coil? Double, increases. By winding another line of turns above the original one end in the same direction. It means that N2 is equal to twice of N1. Which one is bigger, L2 or L1? Absolutely, L2 is bigger than L1. By which factor? By which factor? By factor of 4. So it means that L2 is equal to 4 times L1. Why 4? Because L is directly proportional to the square of the number of turns. So it becomes quadrupled. What happens to the coefficient of self-induction? It becomes quadrupled. What do you mean by quadrupled? It means that it becomes 4 times. Okay? So the last topic in this section is about the eddy current. What is the eddy current? Is smaller or small circular current that produces as a result of changing the magnetic field. What is eddy current? Circular induced current. Okay? Look at this copper. So this metal or this copper, when the magnetic field approaches, what happens to the magnetic field? Increases. Okay? So this increasing of the magnetic field, it goes to changing magnetic flux. So this change of the magnetic flux produces what? Produces the induced current. Okay? So the induced current in eddy current, its shape is circular. So that is why the definition of eddy current is circular induced current. What is the type of the induced current in the eddy current? Circular induced current within a conducting material. Okay? And this induced current produces the magnetic field. So these two magnetic field, the induced magnetic field and the magnetic field of the biomagnetism, they are opposites to each other. So that is why it goes to slowing down the magnetic field, and it goes to increasing the temperature. What are the applications of eddy current? So this is very important, be careful. The eddy current can be used in a furnaces Why? Because according to this eddy current, this changing of the magnetic field, so this induced current, it goes to increasing the temperature. And in a car brake system, the car brake system can be used by the eddy current and detecting metals in airport and in underground. So this for applications of the eddy current. What are the disadvantages of the eddy current? Some of the energy is loses the kinetic energy due to the motion of the conducting material inside the field is thus converted to what? To the heat energy which distribute within the material. So explain how eddy current produces. As I told you, when a conducting bar moves in a magnetic field, the electromagnetic induction that arises due to the variation of what? Magnetic field. Or due to the variation of magnetic flux or magnetic fields. So the magnetic flux leads to induce what? Circular current. Okay? Within the material that resists the original variation of the flux. This phenomenon is called what? Eddy current. So the inside story is skip it. And this is also skip it because related with the inside story. Okay, so let's solve the questions of the section review. Section 1. We finished section 1 in chapter 6. Now we're going to solve the questions in the section review. Question 1, a circular current loop. A circular current loop made of a flexible wire is located in a magnetic field. Describe 3 ways. We solved this question by moving the loop into or out, rotating the loop, changing the strength of the magnetic field, and changing the shape of the loop or size of the loop. Question 2, also we solved this question in a previous lesson. When in the case move away to the left to the magnetism, you can find the direction of the current. And this question also is easy question. Number of turn. The coil is pulled steadily out. It means that B final is 0. Okay. By changing the magnetic field, you can find the induced EMF, and the result is positive. Why? Because the magnetic field decreases. Okay. So we finished this section. Hope you get the benefits from this explaining. Hope you enjoy the lesson. Thank you very much for the listening.